Hello, welcome to today's class, and as the first slide exhibits, we will discuss today Fourier series. The complete class of more than half a minute includes introduction about Fourier series, definition of Fourier series, then evaluation of Fourier coefficients, and then we will discuss sine and cosine series. Since it is a new topic, we will see what is background of the topic. In physics, we always came across the problems including vibrations and oscillations. The examples are vibrating tuning fork, oscillating simple pendulum, the AC electric currents, AC electric potentials, etc. etc. These are the simple oscillatory phenomena represented by sine and cosine functions. For example, an oscillating function repeating with frequency n can be represented mathematically as y equal to a sine nx or y equal to a cos nx. We also call it as equation of simple harmonic motion. We are familiar with this. Similarly, a pure tone of language or pure tone or fundamental tone of a musical instrument like a flute can also be represented by a sine function. However, if it is a complex musical sound consisting of sounds from number of musical instruments and the lyrics or speech, then it has overtones along with the fundamental tone of the instrument, of the music. And in such a case, it cannot be represented mathematically as y equal to a sin nx or y equal to a cos nx. It cannot be represented by a single sine function. Such type of complex musical sound or complex function where there are overtones along with fundamental tones is represented by an infinite series of sine and cosine terms having a period of fundamental tone, and that is called as a Fourier series. So, Fourier series consisting of infinite number of sine and cosine terms having period of fundamental tone. Now, let us define a Fourier series. So, as we have introduced that Fourier series consisting of infinite number of terms of sines and cosines, how it can be mathematically written. So, Fourier series is simply expansion or representation of a function. So, as we have called it in the introduction as a complex function consisting of fundamental tones and lot of overtones. So, Fourier series is defined as expansion or representation of a function in a series of sines and cosines, written as fx. Here fx is a function, fx equal to a0 plus summation n equal to 1 to infinity an cos nx plus summation n equal to 1 to infinity bn sin nx. So This is equation 1 shown on the slide, present slide, where fx has only finite number of extreme values and finite number of discontinuities. Now, what are these extreme values and discontinuities? We will discuss in the next coming articles. But as a definition, we have to remember the equation 1, that fx equal to a0 plus summation from n equal to 1 to infinity a n cos nx, that means infinite number of cosine terms, plus summation n equal to 1 to infinity bn sin nx, that is infinite number of sine terms. So a series comprising of infinite number of cosine terms, sine terms, along with the constant a0. So this is a Fourier series. Now what are a0, an and bn? These a0, an and bn are the constants or coefficients known by the name of the mathematician who discovered this series, that is Fourier. So these are called as Fourier coefficients, Fourier series and Fourier coefficients. So this was the definition, that it is a series which is defined, Fourier series is defined as a representation or expansion of a function in terms of series and cosines, written as fx equal to a0 plus summation n equal to 1 to infinity an cos nx plus summation n equal to 1 to infinity bn sin nx, where fx has only finite number of extreme values and finite number of discontinuities. Okay. So in other words, if function fx has infinite number of extreme values or infinite number of discontinuities, it cannot be represented by equation 1. So the condition is that fx has finite number of extreme values and finite number of discontinuities. a0, an and bn are known as the Fourier coefficients. We are familiar with one property of sine or cosine function, that sine x or cos x has a period of 2 pi. That means after 2 pi it repeats itself. So sine x plus 2 pi, it is equal to sine x. Cos x plus 2 pi, it is equal to cos x. Similarly, sine nx and cos nx shown in equation 1 also have a period of 2 pi. That means sine n x plus 2 pi, it is equal to sine nx, and cos n x plus 2 pi, it is equal to cos nx. So sine nx and cos nx represented in equation, they have a period of 2 pi. It means the complete Fourier series shown by equation 1 has a period of 2 pi, since it is a series represented by sine nx and cos nx. So Fourier series is a function which has period of 2 pi in the interval minus pi to plus pi. Let us evaluate the coefficients a0, an and bn, known as Fourier coefficients. Evaluations of Fourier coefficients. To evaluate the values of Fourier coefficients a0, an and bn, we use the orthogonality property of sine and cosine functions. And this orthogonality property is represented by equations 2, 3 and 4 shown on this slide. Equation 2 is minus integration from minus pi to plus pi sin mx into cos nx dx. It is always equal to 0 for all values of integers m and n, or irrespective of values of integers m and n. Integration minus pi to plus pi sin mx cos nx dx is equal to 0. So first orthogonality property. Second orthogonality property, integration minus pi to plus pi sine mx sine nx dx. So both functions are sine. It can take two values. So it's 0 when m equal to 0 and pi into delta when m is not equal to 0. And the third one, minus pi to plus pi cos mx cos nx dx, which can take two values, 2 pi when m equal to 0 and pi into delta when m is not equal to 0. So these three properties we use to evaluate the Fourier coefficients, and how this can be used and values of Fourier coefficients a0, an and bn are obtained. Let us see. Now we have equation of the Fourier series as equation 1. Again I repeat, I have rewritten the equation here in this slide for convenience. So fx equal to a0 summation n equal to 1 to infinity an cos nx plus summation n equal to 1 to infinity bn sin nx. So this is the Fourier series. Let us multiply this equation 1 by cos nx and integrate with respect to x within the limits of integration minus pi to plus pi, so that we obtain left hand side as integration minus pi to pi fx cos nx dx. So here we multiplied right hand side, that is function fx with cos nx, and we integrated within the limit minus pi to plus pi. Now for first term, that is a0, we have to multiply it with by cos nx. So a0 cos nx and take integration, so minus pi to plus pi a0 cos nx dx. So first term towards right hand side. And second term is an cos nx. Again multiply it by cos nx. So we have an cos integration minus pi to plus pi an cos nx dx. Third term bn sin nx, multiplying with cos nx and integrating, we have minus pi to plus pi bn sin nx cos nx dx. Now look at the left hand side, integration towards left hand side. So integration minus pi to plus pi fx cos nx dx, it survives and it is equal to minus pi to plus pi an cos nx dx. So the two terms towards right hand side, that is first term integration minus pi to plus pi a0 cos nx dx, and the third term minus pi to plus pi bn sin nx cos nx dx. So third term vanishes due to orthogonality property, and first term towards right side vanishes since cos nx has a period of 2 pi. So integration within that will be equal to 0. So in this way we have minus pi to plus pi fx cos nx dx, it is equal to an, and what is integration of minus pi to plus pi cos nx dx? So according to orthogonality property, if n is not 0, it is equal to pi. So it is an into pi, and we have in this way an equal to 1 by pi minus pi to plus pi integration minus pi to plus pi fx cos nx dx. To avoid confusion with the x, we introduce here the new variable phi. So the value of an function coefficient an is now equal to 1 by pi integration minus pi to plus pi fv cos nv dv. Let us call it as equation 5. So in this way we evaluated the value of an. Now initially we multiplied equation 1 by cos nx. Now multiply it by sin nx and integrate with respect to x within limits of integration minus pi to plus pi. So here the term that survives is minus pi to plus pi bn sin nx dx towards right side. And in this way we have bn and integration of minus pi to plus pi sin nx cos nx dx if n is not equal to 0 is equal to pi. So we have integration from minus pi to plus pi fx sin nx dx, it is equal to bn pi. And what is bn? Then bn is equal to 1 upon pi into integration minus pi to plus pi fx sin nx dx. Again, to avoid confusion, we introduce the new variable v for our convenience, and bn is now equal to 1 by pi minus pi to plus pi fv cos nv dv, as it is represented by equation 6 on this slide. In this way we obtained values of coefficients an and bn, and in order to find the value of coefficient a0 let us integrate equation 1 with respect to x within limits of integration minus pi to plus pi. And in this way, towards left hand side we have minus pi to plus pi fx dx, and towards right hand side we have only the first term that survives, that is minus pi to plus pi a0 dx, and second and third terms does not survive since sine and cos are having period 2 pi. So their integration within limits minus pi to plus pi, so within period 2 pi is equal to 0. So we have minus pi to plus pi fx dx equal to integration minus pi to plus pi a0 dx towards right hand side, and integration dx is equal to x within limit minus pi to plus pi, and after putting the limits, that is pi minus in bracket minus pi, it is equal to pi plus pi, so 2 pi, so a0 into 2 pi towards right hand side. And in this way a0 equal to 1 by 2 pi minus pi to pi integration minus pi to pi fx dx. So it is a0 equal to 1 by 2 pi minus pi integration minus pi to pi fv dv, where x is conveniently replaced by the new variable v. So in this way we obtain the values of Fourier coefficients a0, an and bn, and we use the expressions 5, 6 and 7 in the next coming articles and problems while calculating the values of Fourier coefficients a0, an and bn for the function fx. Now after putting the values of a0, an and bn from equation 5, 6 and 7 in equation 1, that is fx equal to a0 plus summation n equal to 1 an cos nx plus summation n equal to 1 to infinity bn sin nx, we find. So here we have replaced a0, an and bn with their corresponding values. So we can combine the second and third terms, and we have the final expression for Fourier series as fx equal to 1 by 2 pi integration minus pi to pi fv dv plus 1 by pi summation n equal to 1 to infinity integration minus pi to plus pi fv cos n in bracket x minus v bracket cos dv. So this is equation 8, where we substituted the evaluated values of the coefficients a0, an and bn, and we obtained this final equation. In Fourier series, we always came across the series consisting of cosine terms only and the series consisting of sine terms only. Let us discuss cosine series and sine series one by one. So first, cosine series. If function fx f of x is even function of x, then we know that f of minus x, so changing sign of x doesn't make any difference, so it is equal to fx. So this is called as property of an even function. That means if fx is even function, then f of minus x is equal to fx. Changing a sign of variable does not affect the function. So in this way we have important integral from Fourier series, that is minus pi to plus pi fx sine nx dx, it is equal to 0. That means Bn is equal to 0. Since Bn is equal to 1 by pi minus pi to pi fx sine nx dx, so Bn is equal to 0. And what about integration 1 by pi minus pi to pi fx cos nx dx? This will survive. And if we convert integration minus pi to plus pi as equal to 0 to pi, it will be 2 by pi 0 to pi fv cos nv dv equal to an. So this is the value of an for this particular series where fx is an even function. So let us call it as equation 10. And what about value of a0? It is equal to, we evaluated already, and it is equal to 1 by 2 pi minus pi to pi fv dv. So it survives again. Let us call it as equation 11. So Bn is equal to 0 when fx is even function, an and a0 survives. And in this way, in Fourier series we have two terms only, that is a0 plus summation from n equal to 1 to infinity an cos nx. And after putting the values of a0 and an, we have a series fx equal to 1 by pi 0 to pi fv dv plus 2 by pi summation n equal to 1 to infinity integration 0 to pi fv cos nv dv. So this is the value of an multiplied by cos nx. Now important to note here that this is a series consisting of only cosine terms, and hence it is called as cosine series within the interval 0 to pi. So this is about the cosine series. In summary, we can say that if fx is an even function, then the property f of minus x equal to fx, and in that case the value of Fourier coefficient Bn reduces to 0, and we have a series of cosine only, and that is called cosine terms only, and that is called as cosine series. Similarly, if fx is an odd function of x, then changing sign of x to minus x will change the function to a negative function, that is minus fx. So f of minus x equal to minus fx if fx is an odd function. And in that case, we find that the value of integration minus pi to pi fv dv, it is equal to 0, so a0 equal to 0. Minus pi to plus pi fv cos nv dv, again equal to 0, since fv, that is fx, is odd function, so an also equal to 0. So a0 and an both are equal to 0 for this fx as an odd function. And integration 1 by pi minus pi to pi fv sine nv dv, that is Bn, it survives. And if we convert integration minus pi to plus pi to 0 to pi, so it will be 2 into integration 0 to pi. So 2 by pi into integration 0 to pi fv sine nv dv will be Bn. So a0 equal to 0, an equal to 0, only Bn remains. And in this way, Fourier series has a single term, and it is fx equal to summation equal to n to infinity Bn sine nx. And by putting the value of Bn, we have 2 by pi summation n equal to 1 to infinity. So here we substituted the value of Bn, that is 0 to pi fv sin nv dv and sin nx as it is. In this way, it is the Fourier series which has sine terms only. Hence, it is known as sine series in the interval 0 to pi. In summary, if fx is an odd function, then f of minus x is equal to minus fx, and a0 and an both become 0 and only bn survives, and we obtain a Fourier series as a series of sines only, and it is known as sine series in the interval 0 to pi. So, with the introduction of Fourier series to evaluation of Fourier coefficients, and with the two simple series, sine series and cosine series, we conclude today's class. Thank you for paying attention and listening. Thank you for your patience. Thank you very much.